All right, lights, camera, action. Here we go. Welcome to another exciting episode of AP Chemistry. Today is, hard to believe, Monday, November the 17th. Y'all, good news. We only have this week, and then we get a whole week off. Bad news is we got to finish this unit, take a test, and make sure that we understand all of these things about bonding, ionic and covalent bonding, metallic bonding, be able to draw Lewis dot structures. And then the stuff we're going to talk about today is how do we tell really if a molecule is polar? What are the criteria? We've just kind of talked about phone call in the past, but then we're going to add in a second criteria to that based upon our Lewis dot structures. You will have to know your shapes based upon the Lewis dot structures. Oh, what else? Did everybody get one of these molecular geometry sheets? Have I given you one of these? Okay.
Yeah, while he's passing them out, make sure to hit that like, smash that subscribe button, ring that bell.
Do we have to memorize those?
Yes.
Probably after our relation.
So I have to remember the
Anybody else need one? Speak now for a vote, please.
Wait, Mr. Hobbs, do we need to like?
Yes.
And the hybridization?
Yes. The hybridization is going to be easy. So let's talk about this. Okay? Hybridization. Remember, you take a red rose and a white rose, hybridize it, you get a pink rose. Or a red polka dot rose. Okay? So we get something that's in the middle. You take an s orbital, hybridize it with a p orbital, and you're going to end up getting this hybrid fat orbital. Okay? Now, the hybrid orbitals are what determine the actual shape of the molecule. That's going to form your sigma type bond. Okay? The pi bonds are your side to side. Only p orbitals can form a pi bond. So when hybridization occurs, if you have double or triple bonds, not all of the p orbitals can hybridize because some have to remain unchanged to form the pi bonds. Okay? So if I look again at that crazy molecule that I drew, well, actually, I think I just did a double bond here, triple bond here. Okay? Okay, so if I look at this molecule right here, first off, I can count sigma and pi bonds. If it's a single bond, it's what type?
Sigma.
Sigma. Sigma, 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 pi. Sigma, 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 pi, pi, sigma, 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 sigma. So that's the first thing. That's easy to determine whether it's a sigma or a pi bond. Now, in terms of hybridization, if you're looking at that sheet that I just passed out, or if we know anything that is AX4, AX3E, AX2E2, okay? Anything that is like that is always going to be sp3 hybridization, okay? sp3 hybridization is always going to be, the hybrid orbitals are always going to be in the shape of a tetrahedron. Well, actually, okay, so this is the big one that kind of shows these are your four hybrid orbitals. If we look just at these models, it's in the shape of a tetrahedron. The bond angle here is always equally 109.5 degrees. Four things that hate each other get maximum distance apart, 109.5 in all directions. This one tries to push apart, that pushes them closer together, 109.5. But if one of them's a lone pair, like an ammonia, okay, now it's still 109.5 is the base angle, but now we only play dot to dot with the nuclei that are present, and so we say it's AX3E. The shape is a triangular based pyramid, trigonal pyramidal, but what about the bond angle?
Probably like 2 greater because the electrons.
2 greater?
2 less.
2 less. Because lone pair occupy a greater space than bonding pair. Now it's 2 to 3 degrees approximately per lone pair. So the bond angle for ammonia, the exact bond angle is 107.3. but every AX3E is going to be different based upon how big these other atoms are and you know, all the different factors that go into it. Okay? Now, when we go to water, H2O, we have AX2E2. So again, it doesn't matter if you put the two hydrogens straight across from one another, you're going to be looking at it like this with no depth perception. So you got the hydrogen, the oxygen, the hydrogen, okay? But the reality is it's bent, and so the oxygens are pulling, the oxygens are pulling from the hydrogen this way, so they don't cancel each other out. So it's going to be a polar molecule, okay, because it's bent. But the bond angle now is down 104.5 degrees. 2 to 3 degrees per lone pair. Since we have two lone pair, it's 4 to 6 degrees smaller. Okay? And again, you just need to know approximate. You don't have to know. You just say, you know. Now listen, don't put a range. If a problem ever asks for, and this is a nitpicky thing on AP, if they ever ask for a bond angle, you just guess something, you know, 105, 104, 103. You know, they're going to give you credit for anything in that ballpark. Don't put a range. Don't say something less than 109.5. Because how less? Is it down to 90? Is it down to 80? You know, yeah, I would just say 103. You know, but you don't have to don't give a range. Give an exact number. Okay? And they're very liberal in what they accept as far as those values. Okay? But you need to know 109.5 is the base. That's all sp3. Anything that's sp3 hybridization is going to do that. Anything that is AX3, AX2E. Notice I'm not going to AX. AX is always just going to be linear. Doesn't matter if it's just two atoms, it's always linear. We don't really worry about hybridization there. But anything that adds up to 3 is going to be sp2 hybridization. Well, that's going to be, this is, okay, the law of conservation of orbitals. We have 1 plus 3 makes 4. We have 4 hybrid orbitals, so they're going to be at the points of a tetrahedron. Here, we're going to have 3 hybrid orbitals. So it's going to be at the points of a triangle. So again, when I look at this one here, you can see the triangle. Here's your carbon undergoing sp2 hybridization. These are your 3 hybrid orbitals at the points of a triangle, trigonal planar. Planar meaning flat. Okay? And then you have your 1 p orbital non-hybridized that's going to be perpendicular always to the plane. And then that side-to-side overlap is your pi bond. And then anything that is just AX2, okay, is always going to be sp hybridization. These are always. Now, for any, if it's not every single time, there might be one in the 29 years I've been doing this, okay? Almost always, they're going to give you a compound similar to this, not this complex, but something like this. They're going to point to a carbon and say, what's the hybridization? All you have to do is identify it. You don't have to explain what it's doing. You don't have to go through the ground state, excited state, hybrid state. You don't have to do anything. You just have to state the type of hybridization. So if I look at that carbon right there, what's my AX formula around that carbon? AX4. So what type of hybridization is it? sp3. So all you would write is sp3. It says identify the type of hybridization on this particular carbon. It says identify the type of hybridization. You don't give an explanation. You don't go into AX anything. You just write sp3. Okay? But if I look at these two are both doing the same thing. What's the AX formula around each of those carbons? AX3. A, 1, 2, 3. A, 1, 2, 3. AX3. So what's the type of hybridization? sp2. Notice that 2 plus 1 equals 3. 3 plus 1 equals 4. Okay? Anything with a triple bond? Automatically. sp. Man, I should have worn that shirt today. Yes, we are sp. Okay? And I have a flask that has all the S compounds with sp hybridization in it. So you wear it, you know, says, oh man, what does it mean? We are sp. But it's obviously Spain Park, but you know, to understand the actual chemistry part of this, you wouldn't understand. You have to take AP Chemistry to know that. You know, I could try to explain it to you, but you probably wouldn't get it. You know? That's what you tell your friends when they ask you about it.
Why do you say E on the
The E is the number of lone pair electrons. Okay, the number of lone pairs. So if I look at ammonia, ammonia looks like this. This is going to be AX3E. That is my E. Okay? Now, notice though, still on this, AX3E. This is telling me the number of electron pair domains. That's another key AP word, that the phrase that they like. Electron pair domains. In other words, how many different places around the nucleus are the electrons hanging out? Lone pair count as an electron pair domain. They don't count towards molecular shape, but they still affect the shape because they're still occupying a space. Okay, so when I have these two lone pair, this is not a linear molecule because these two lone pair are still occupying this space, repelling and keeping these from going linear. So we still have 4 electron pair domains here, even though there's 2 bonding pair, 2 lone pair. But we still have 4 electron pair domains, and it's the number of electron pair domains that determines the overall shape. Okay? This AX2 has 2 electron pair domains. This has 3 electron pair domains. These all have 4 electron pair domains. Obviously AX5, AX4E, AX3E2, AX2E3 all have how many? 5 electron pair domains. So something with 5 electron pair domains is going to have a different shape than the 6 electron pair domains, because 6 electron pairs have to arrange themselves differently than 5 electron pairs.
Why can't they hybridize? Like, why can't they have hybridization?
I don't know. I was going to try to make something up. They used to call it sp3d and sp3d2 hybridization, but experimental evidence says that they don't. And I've never been able to read, or they may have at this point have a new theory on how expanded octets form in terms of how the orbitals rearrange. But as of my last reading, which was a few years ago, they didn't really have a good theory on how expanded octets form. We just know they do. Sorry to disappoint you that I didn't have the answer to everything. I disappointed myself. I'm going to have to go do research. Maybe over Thanksgiving. That'll be my leisurely reading. Okay, so listen, we can identify the hybridization method. So in your notes, if I just gave you this, okay, if I just gave you a compound that looked like carbon 1, carbon 2. What's the hybridization on carbon 1? What's the hybridization on carbon 2?
SP2.
Okay? SP3, SP2. That's all you have to know on hybridization. Now, I could have told you just to memorize that. But if it has 0 meaning, then what good is it? Just memorize it. We're here to learn. We're here to have a foundation of what's going on in chemistry. Okay? So it's worth a day for us to be able to understand that, but that's really all you have to be able to do. Identify the type of hybridization.
So we're not gonna have to draw like models.
Nope, and I never make you draw the shape because I can't draw a 3-dimensional shape. Now, when you get to organic chemistry, they make you do little dots and going away, and you have to kind of draw 3-dimensionals. And I struggled with that a lot, but I had a thing of models that I could build and kind of visualize it and see. Okay, but have you ever taken the aptitude test where they give you the little squares with dotted lines and they say fold it and what shape would it make? Have you ever had to do anything like that to where you have to have your spatial aptitudes where you have to be able to follow? Even trying to put these darn white boxes together where they give you the directions and tell you to fold this side up, fold that side up, this, that. I mean, I struggle majorly with my spatial. That's just not a gifting that I have to be able to visualize what it's going to look like based upon how I'm supposed to fold it and make into like origami, all the different shapes. Okay, so I have to have models. That's why I have all these models out here so I can see it to visualize it. Okay, so that is both hybridization and the valence shell electron pair repulsion theory. Those two things go together. The number of electron pair domains determine the shape. The hybridization determines the number of electron pair domains. Pi bonds are not considered an electron pair domain. So a double bond is just one electron pair domain because they're still between the two atoms. A triple bond is one electron pair domain. Okay? So again, when I do this, this just is AX2, there's just two electron pair domains around the carbon. Okay? A triple bond just counts as there are electrons between the two carbons and electrons over here. There's two electron pair domains. So two things that hate each other are going to get 180 degrees apart. And then the pi bonds are just secondary bonds. Okay, now let's go back to SO3. SO3, when we drew it, it looked like this. And we had 24 electrons. And we all said, okay, now my central atom is lacking. So what do I have to do? Form a double bond. So where do I steal the electrons from? Any one of them. When you have options on your double bond where you can steal the electrons from, we have a thing called resonance. To where I could have made it look like this, or I could have made it look like this. Okay? So which one is it? All of them? What that, in band, what does it mean when sound resonates?
It's like it like
Overlap.
yeah, it like kind of like
If my voice is resonating down the hall,
Echoing.
echoing, and what's an echo? Bouncing back and forth, right? Resonance is a horrible name for this. Because with the term resonance, we would assume that the double bond is resonating or flipping between all three spots and kind of rotating around. The reality is that's not what's happening at all. Okay? Now, I'm going to go deep here. Get ready. Okay, this is AP Chemistry. We're going to talk about the bond order or the bond strength. Okay? If you have a single bond, it's got a bond order of 1. If you have a double bond, it has a bond order of 2. Okay? Do I need to repeat that?
Yeah.
If you have a triple bond,
No, go back.
it has a bond order of 3. Okay?
are there quadruple bonds?
No, there are not.
What's a single bond?
Okay? Because in order to have, okay, it's a 2. Okay? Just make sure, that's right. I know, I went fast. Okay? Now, you cannot have a quadruple bond because you're out of p orbitals. Only p orbitals can form pi bonds. Okay? And so you have to have the s and the p hybridized. Now you only have 2 p orbitals. You only have x, y, and z axis left. You're on the x axis with your sigma bonds, so your pi bonds can only be on the x, on the y, and the z. Okay, so you're out of p orbitals, so you can't have a quadruple bond. Okay, so triple's as high as you go. Now, in this molecule, though, when you study this molecule, it turns out that the bond order between the sulfur and the oxygen, all 3 have the exact same bond order. And that it is stronger than a single, weaker than a double, that the bond order turns out to be around 1.33. Okay? That all 3 of these are equal here. So the double bond isn't flipping back and forth where sometimes it's a double, sometimes it's a single, sometimes it's got a bond order of 1, sometimes bond order of 2. They all have a bond order of 1.33. So what happens is, should have had this built. I gotta find the right one. Gotta find the right one. Gotta find the right one. It's not the right one. I know. I should have had this built. Where's the right one? Y'all are so obnoxious. Have I told you lately how much I hate you? How can there not be one in there? Here it is. Okay. I'm out of time, I lose.
Wait, how do you do
I didn't realize that this was going to be show choir chemistry. All right. I hate to interrupt this performance. Okay.
Alright, okay, we're free.
Yeah. If that track scholarship doesn't work out for you, you have an alternate here. You can be in show choir at college. Okay. All right. So here's the deal. SO3. SO3. First off, what type of hybridization is this going to be? What type of hybridization is it going to be?
SP2.
Okay, over here, this side, over here. What type of hybridization is this going to be? SP2. Okay, good answer, Maggie. All right, so SP2 means that I have a hybrid orbital, hybrid orbital, hybrid orbital, and then the oxygens are going to come in here with their p orbitals and bond with the p orbital and bond with a p orbital. Okay, but each sulfur though, what's AX3? This is my.
That's around on the board.
What? You guys need to go back to the jungle. Okay. Here we go. So your SO3 is going to have 3 hybrid orbitals, AX3, okay? Sigma bonds, trigonal planar. But they're going to have a non-hybridized p orbital perpendicular. So normally a pi bond is just going to be the overlap side to side of the 2 perpendicular p orbitals forming the pi bond. But when you have resonance, you have a big pi bond. You have a multiple overlap of p orbitals because this oxygen and this oxygen both have p orbitals perpendicular to the plane. So this is a lone pair, this is a lone pair, this is 1 electron, this is 1 electron. But instead of just having a 1 p orbital side to side, all 4 p orbitals, and you get a cloud above, and you got to realize the p orbital's got the lobe below it, a cloud below, and the electrons get delocalized, and they get shared equally. So you have 2, 4, 5, 6 electrons all being shared equally, delocalized, and have this cloud of pi electrons above and pi electrons below. And as a result, we end up having this thing called resonance where the double bond is actually shared equally by all 3 atoms. So the bond order is no longer a double or a single, it's a 1 1/3 bond order because it's being shared. Now if I make one of these a lone pair, okay, this is a lone pair, Now, the shape is just going to be bent, but you still have this occupying the third electron pair domain. But now the double bond is just going to be shared, okay? And if I take this off, now there's not a double bond there, it's just a lone pair. Now we're just sharing between these three. So now what's the bond order if it's just SO2? If it's just that, whoops. It's just sulfur.
Just one. That's not a position.
Third time's a charm.
Okay.
Okay, so now if it's SO2, it's AX2E. What's my hybridization still? sp2. It's still in the shape of a tetrahedron, it's just one of them's a lone pair. Okay, but now I only have the double bond only can be in two different places. So what's my bond order going to be? 1.5. Okay? 1.5. So resonance, the most common thing that resonance is in benzene C6H6. So if I look at this carbon right here, what's my AX formula on this carbon? AX3. You notice A's got a double bond. Here's A, 1, 2, 3. Okay? So but this one here too. So when I draw,
So it's got a lot of residue.
when I draw benzene, C6H6, okay, it turns out to be in a ring. Gentlemen, come on. Time to focus. I put a hydrogen, a hydrogen, a hydrogen, a hydrogen, a hydrogen, and a hydrogen. But each carbon can form 4 bonds. So I need to form a double bond, a second bond. Okay? Now, if I go here, now this carbon has 1, 2, 3, 4. This carbon has 1, 2, 3, 4. It would be alternating double bonds. But I could just as easily have said hydrogen, 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 hydrogen. I could easily put the double bond here, here, and there. So again, we have resonance occurring. Now if I want to figure out my bond order, you can count, there's basically 9 bonds in 6 places. So it's 1.5. Another way you can think about it is that this one is being shared there, that one's being shared there, this one's being shared here. So each double bond is being shared in 2 spots. So everything has a sigma bond, a 1, plus then they get half of the double. Right? 1.5. 9 bonds in 6 places, or you can just kind of see that, you have, again, in the SO3, you have 4 bonds in 3 places, 1 and a third. Or you can think of it as the double bonds being split into 3. So they all have a sigma bond, a 1, plus then they get a third of the double, 1.33. But the key with resonance is all the bonds are the same. All the bonds are the same. You don't have one shorter, longer. By the way, a single bond is longer than a double bond. Double bond is shorter. A triple bond is the shortest. The more you have in common, the closer you are. Okay? So bond lengths, bond strengths are all the same when you have resonance. Anytime you can put the double bond in more than one place, you have resonance. Okay? So this is, and we'll look at practice problems on this, but that's a big concept. Okay? All right. So on this worksheet, really, it went off? if I look at HNO2, is there potential for resonance in HNO2? Look at your Lewis dot structure. You already drew it.
Yes.
Yes. Yes.
No.
Actually, no.
No, there's not.
Why not?
The hydrogen has to be
Okay, so we have nitrogen, oxygen, hydrogen, double bonded oxygen, right?
Yeah.
It looks like that. Okay, so when we went and had it like this, okay, when we did our original structure, nitrogen is electron deficient, okay? Do I have choices on where to pull the electron from? We only got one choice here, so we go double bond. But what if it was just NO2 minus?
Didn't even have direct resonance.
Okay, so then it's going to look like this, right?
Yes.
So now I have a choice, don't I? So NO2 minus, I could go here, and whenever you draw resonance structures, you draw a double arrow, and then you would say NO2 minus. And because it's an ion, we put it in a bracket. What's my bond order going to be? 1.5. What about my bond lengths? They're going to be the same. Bond strength is going to be the same. Okay? Now, what about if I did? Okay, this is an AP question. It actually just showed up again. It was a very old one. What if I just wanted to draw NO2? NO2. Count electrons. Try again. 17 electrons. So we go 1, 2, 3, 1, 2, 4, 6, 8, 10, 12, 14, 16, 17. Ooh. If you ever have an odd number, it's called a free radical. Now, if you ever listen, that the nutritionists always talk about free radicals being in your body. They're highly reactive. They do bad things inside of you, cancer and other diseases, because of their reactivity. So you want to take antioxidants. Antioxidants are things that are reducers. They have extra electrons. You want to tie up the free radicals. You want to get them out of your body. A free radical. Now, you treat this just like it's an AX2E. You treat the one electron just like it's a pair. Still electron pair domain. However, you don't have the electron-electron pair repulsions, okay? The electron-electron repulsions, and so it doesn't occupy, so it's not going to close the bond like a pair would. So that bond angle is going to be much right at 120. It's not going to be any less, okay? But do I have resonance? I have 2, 4, 5, okay? I'm still going to need to get a double bond and get close to 8 as possible. So yes, I'm still going to have resonance. I'm just going to have that. And you don't need brackets because it's not a charge. But what about NO2 plus? So how many electrons? This had 18 electrons. That's got 17. This is going to have 16 electrons. Okay? So again, now it's going to be that. Whoops. Okay? So now we're going to have this when I draw it. Starting there. 2, 4, 6, 8, 10, 12, 14. 2, 4, 6, 8, 10, 12, 14, 16. So I need 2 double bonds. Okay? Do I have resonance here?
No.
No.
Okay, it's all the same.
It's all the same. Okay? So now I have this, and I have this, whoops, and I'm not drawing all the resonance structures, and I have this. 2468. Okay, it's going to look like that. Those are my three possibilities. This is my NO2 minus, my NO2, and NO2 plus. What's the shape of NO2 plus? Linear. AX2. Okay? What's the shape of NO2 minus and NO2? Bent. Which one's going to have the larger bond angle? The larger bond angle is going to be, I heard, what are you guys saying? NO2. Anybody over here going to venture a guess?
NO2 minus.
Good guess, but it's not. Why would NO2 be a larger bond angle than NO2 minus?
There's no electron propulsion.
Okay, so this electron cloud is only going to be here. This one is going to be occupy a much greater space, which is going to push these a little bit closer together. So this is going to be right at 120 because the AX3 is 120 trigonal planar is what it's based off of. This one is going to be a little bit less, 119. Now it doesn't really go 2 to 3 degrees on those because you already have 120, so it's not as crowded to start with, but it is going to push it just slightly smaller. That was an AP question in the 90s, and then it just showed up like last year, 2 years ago, 3 years ago, somewhere in that range. I just saw it again. Okay?
Great.
Good question. All right, we can take a break. Go ahead and hit pause. All right, so now we understand how to draw Lewis dot structures. Now we understand about how to determine the shape from the Lewis dot structure. We understand resonance. Okay, little side note, but again, that's going to affect the properties of the molecule. Molecules that have resonance tend to be a little bit more stable. Okay. Just for instance, when we talk about a benzene ring, okay, a benzene ring, each carbon, okay, each carbon is what type of hybridization? Okay, it's sp2, so it's trigonal planar, so it's a flat molecule. So the reality is that we have a p orbital on each carbon, and you get 6 p orbitals overlapping side to side. We get this cloud of pi electrons above and below. We have resonance occurring. Okay, so the electrons no longer are localized between the two carbons. Now those pi electrons can go anywhere in here. Okay, gives extra stability to the molecule. Normally, if I was going to add chlorine to this, normally it's going to do what? Oh, not Cl. Try that again. Okay. Normally, it's going to want to break the double bond and do what we call an addition reaction, where we would end up substituting and breaking the double bond, and you'd put a chlorine here, and you'd put a chlorine onto that one, and you now break the double bond. But because of the extra stability due to resonance, when you go to add chlorine to this, the double bond doesn't want to break. Instead, we do a substitution reaction, and we end up getting HCl and H and Cl as my products. So you get it chlorinated, but it keeps the resonance in play. It just adds extra stability. Now that's 100% oh my information, but that just kind of what resonance adds extra stability to it. So when you do, and this is a lot of organic chemistry studies, all that kind of stuff there. Okay. So let's talk about then polarity. Polar molecules, and where are we on the notes? What page? Everybody turn to where it talks about polar molecules.
Four.
Okay, it's right after resonance.
After valence shell electron pair repulsion.
Okay, now, but we've already talked about the valence shell. Valence shell electron pair repulsion theory and hybridization all kind of go together. The valence shell electron pair is based upon the number of electron domains. That's going to determine the shape. Okay, so what really determines whether a molecule is polar or not? There are two criteria for polar molecules. Polar molecules must must. Number one, contain at least one polar bond. This is what we're going to use phone call. That's how we determine if it's got a polar bond or not. Now, the reality is we look at the difference in electronegativities. We looked at the periodic table. On the back side of the periodic table, it's got the percent ionic character based upon the difference. When is the only time you're going to have a perfectly non-polar bond? Diatomic, when it's zero difference in electronegativity. Now, generally, less than 4 difference, or 0.4, I should say, difference in electronegativities, then it's still considered pretty much non-polar. Okay, we have different degrees of polarity. So the farther apart geographically they are in the periodic table, remember fluorine is your most electronegative element. Oxygen's number 2, chlorine and nitrogen are number 3 and 4. Okay, those are your big 4, so they're generally going to have the biggest difference in electronegativity. But it's not really until you have exactly the same 2 elements is the difference 0. Now, you are never going to be expected to have electronegativities memorized. We need to know the trend, but you never have to have exact values. That's why phone call works. Okay? So you have to have at least one polar bond. That's all we've looked at so far. That's review. But the second criteria is that the molecule must be asymmetrical. Okay? The molecule must be asymmetrical. Now this is where it gets tricky because when we draw our Lewis dot structures, it could be deceiving. You have to trust our rules here. Okay? Asymmetrical molecules. Now this has to be and, not an or. This is an and. It's not one of the others. Both of these criteria have to be true for it to be a polar molecule. For A, if it's asymmetrical, okay, all the bonding atoms the X's in our AX formula are not the same. Okay? All the bonding atoms are not the same. Now, it doesn't matter if there's lone pair or no lone pair. If the X's aren't all the same, it's going to be asymmetrical. Because they're going to have different poles for the electrons. They're going to have different electronegativities. B, this is an or. I'm going to say most, I'm going to change my wording from what I've done in the past. Most shapes that have a lone pair of electrons on the central atom are asymmetrical. And just a little tidbit here, when you're going to spell the word asymmetrical, don't be an ass. Okay, there's only one S in asymmetrical. Okay, so if you see that you're spelling that word, you're spelling it wrong. There's only one S in asymmetrical. I see some erasing. All right, now look, I used to kind of say that if there's a lone pair on the central atom, then it's going to be asymmetrical. But people misinterpret that as the lone pair is making it asymmetrical. It's just that most shapes, most molecules that have a lone pair on the central atom, they're asymmetrically shaped. So the answer is always it's asymmetrical. It's an asymmetrical bent shape. It's an asymmetrical seesaw shape. It's not asymmetrical because it's got a lone pair on the central atom. That answer doesn't fly. It's asymmetrical due to the shape. It's just that most shapes that have a lone pair on the central atom are asymmetrical. However, 2 exceptions. Always got to be an exception. Okay, which is why we can't say if it's got lone pair, it's going to be asymmetrical, because there's exceptions. Okay, AX2E3 is linear and symmetrical. Assuming the two x's are the same, the two x's still have to be the same for it to be symmetrical, and AX4E2, which is square planar. Again, the x's still have to be the same though. If the x's aren't the same, then it's going to be asymmetrical. Now, in order to have a polar molecule, you have to have a phone call, generally speaking. There are some cases when potentially, like even H2S, it's bent, it's slightly different. It's going to be polar, but it's going to be fairly polar. Okay? Just a term. Dipole moment. Have I shown you that term before? What does that mean? It's a term. It's a measure of a molecule's polarity. The greater the dipole moment, the more polar it is. Okay? So if something has a measurable dipole moment, that means that it's polar. Okay? So let's look at your worksheet. Okay? The Lewis dot structure worksheet. So if I go SO3, okay, so now technically we have all three drawn, okay, but we'll only look at one. Do I have a polar bond?
Yes.
Yeah, because of oxygen, right? So I know I actually have three polar bonds. But is the molecule symmetrical or asymmetrical? How am I going to know? Okay, you can't just look at your Lewis dot structure, because first off, you may not have drawn it in a triangle like that. Okay? All the x's are the same. Okay? Trigonoplanar, and all the x's are the same. And they're, again, most shapes that don't have lone pair on the central atom are generally symmetrical. They're kind of the converse of what I wrote. So what's happening is the electrons are being pulled this way by the oxygen. By the way, electronegativity and atoms attraction for a shared pair of electrons. This is a tug of war for these two electrons. Who's winning the tug of war? In a covalent bond, okay, one's not able to take it away, but oftentimes the flag isn't sitting right in the middle. One team is winning, okay, more than the other, okay? Squid Games here, okay? Nobody's losing, okay? Ionic bonds, somebody loses. Here, nobody loses. So the electrons are being pulled this way more strongly, and they're being pulled this way. But if I pull at 120 degrees, if I pull this way, and that way equally, the net result is no motion. Anybody take physics? Anybody in here in physics? Okay, the vectors, you got your resultant, or your three vectors. The resultant here is zero, because they're all going to cancel each other out. Okay? And so it's that they're all, so the net result is no motion, so the electrons are all evenly dispersed. Okay? So the definition of something polar means it's an uneven distribution of electrons causing a positive and negative end of the molecule to form. It's due to the uneven distribution of electrons. So is this going to be polar or nonpolar? Nonpolar, because it's a symmetrical molecule. Okay, so when you're doing here, we can state the type of hybridization now. We can state whether the molecule is symmetrical. So I want you to go ahead and do that on the paper. I'm going to give you a second grade on this. Okay? I have to say that and make you actually write it down. Okay? And we can state whether the molecule is now polar or nonpolar. Okay? So you should be adding in three things. Hybridization, whether the molecule is polar, and symmetrical or not. So if I look at HNO2, now this is an important thing here. Okay? We have two shapes on this. Each central atom gets a shape. What's the shape around the nitrogen? Bent. Okay? And the shape around the oxygen is bent. Now what's the difference going to be? Bond angle, because one's AX2E, the other's AX2E2. 3 electron pair domains versus 4 electron pair domains. This is off of a 120 degree trigonal planar. This is off of a tetrahedron, 109.5. 2 lone pair though, it's going to be down somewhere around 105. Okay? This is around 120, maybe a little bit less because of the lone pair. But is it symmetrical or asymmetrical? Asymmetrical. Do we have polar bonds?
Yeah.
Yes, so it's going to be polar. Probably more so around this one than around this, because these two are both highly electronegative. But the electrons are being pulled this way. And when we talk about acids and bases, we'll talk about the strength of that there. SiO2. Okay? You may have drawn SiO2 to look like this. And that's 100%, that Lewis dot structure is 100% fine. Do I have polar bonds?
Yeah.
Yeah, because oxygen. But is it symmetrical or asymmetrical? How do I know? AX2, the X's are both the same. It's linear, because we know it's that. So, and then here's the cheat. You don't say this in your answer. I gotta stress this so much. You don't say this in your answer. You don't say this in your answer. But you keep it inside knowing that this is how you tell. But it's not part of the answer. There are no lone pair on the central atom. And the X's are the same. That tells me it's symmetrical. You put in your answer, because of its symmetrical linear shape, it is a nonpolar molecule. Because of its symmetrical linear shape, it's symmetrical. But you know the shapes are symmetrical when they don't have a lone pair on the central atom and the X's are the same. But you don't put that in your answer. Okay? It's not the lone pair making them symmetrical or asymmetrical. It's the shape.
Did someone put it in your answer?
Every year, even after I scream it. And you get it wrong. And you don't get points on AP. Even though I'm stressing it with everything in me. And again, I'm being passionate, not angry. All right, so let's take the last 10 minutes and go through and do this. Try to fill in these things on this sheet. Okay? Have a great day. Go Jags.